Today, we will look at some problems about uniform flow in open channels. For the first problem, we need to clarify the flow in open channel flow scenarios. So for the A, constant flow in a long prismatic channel with a mild slope. So the flow should be a steady, uniform flow. For B, a flow in the transition of the channel in part A to a channel with a steep slope. So the flow should be a steady, varied flow. For C, the flow on a sloped parking lot during a uniform intensity rainfall event. So this should be the steady, varied flow. D, the flow on a sloped parking lot during a rainfall event that decreases in the intensity over time. So the flow should be unsteady, varied flow. E, the flow in a prismatic channel from a rapid opening sluice gate. So this should be the unsteady, varied flow. For the F, the flow during the dry season in an urban stream. So this should be a steady, varied flow. So we have done this problem. For the second problem, a concrete channel with an usual cross section in this figure and it carries water at a flow rate of 30 cubic meters per second, and we need to determine the channel slope. And from this figure, we know the length of this side equals 3.6 meters, and the length of this side equals 1.6 meters. So we can determine the length of this side equals 2 meters. Also, we can determine the length of this side equals 2 meters too. So now, first we need to determine the flow area A. So A equals 4 meters times 3.6 meters minus 1 over the 2 times 2 meters times 2 meters. So the flow area equals 12.4 square meters. And then we need to determine the weighted parameters P. The P equals length of this side 3.6 meter plus the length of this side is 2 meters and plus the length of this hypotenuse. So the length of this hypotenuse equals the square root of 8 meters and plus length of this side equals 1.6 meter. So the value equals 10 meters. And then we know the hydraulic radius RH equals A over the P. So equals 12.4 over the 10. So the value is 1.24. And since we know this is a concrete channel, so from the table 6.2 in the textbook, and the Manning's coefficient for the concrete channel M equals 0.013. And from the problem, we also know the Q equals 30 cubic meters per second. So, and according to the Manning's equation, Q equals 1 over the n times a times r h to the power of 2 over 3 times s to the power of 1 over the 2. So we can determine that the s equals 0.000742. So we have done this problem. For this problem, a 3-meter wide rectangular irrigation channel carries a discharge of 50 cubic meters per second, and the channel has a slope of 0.041, and the Manning's coefficient m equals 0.022. We need to determine the normal depth using the successive substitution method and the figure 6.4. And we know this is a rectangular channel, and the width b equals 3 meters. And we assume that the normal depth is ym. So we know the flow area A equals b times yn equals 3 times yn, and the weighted parameter P equals b plus 2 times yn. The value is 3 plus 2 times ym. And we also know the Manning's equation Q equals 1 over the n times a times h to the power of 2 over the 3 times s to the power of 1 over the 2. And we also know the hydraulic radius RH equals a over the p. So we can get that the Q equals 1 over the n times a to the power of 5 over 3 times p to the power of -2 over 3 times s to the power of 1 over the 2. And we this is the Q, and we rearrange this equation so we can get that the A to the power of 5 over 3 times P to the power of -2 over the 3 equals n times Q divided by the s to the power of 1 over the 2. And we know the A equals 3yn and P equals 3 plus the 2yn, and the n equals 0.022, and the Q equals the 50 cubic meters per second, and the S equals 0.041. So we can get that 3ym to a power of 5 over 3 times 3 plus 2ym to a power of -2 over 3 equals 0.022 times 50 over the 0.041 to a power of 1 over 2. So this value is 5.43. And then we use a successive substitution method. We get that the ym equals approximately equals 2 meters. And from the problem, we also need to determine the normal depth from the figure 6.4 in the textbook. And this is a figure 6.4a in the textbook. And we know the x-axis is the value of this equation. And for this problem, we know the n equals 0.022 and the q equals 50 cubic meters per second. And the km in the international unit system, the km equals 1, and S0 slope for this problem is 0.041, and the b equals 3 meters. And now we can determine the value of this equation for this problem. Is the 0.29, and we roam in this 0.1, 0.2, maybe this at this location is 0.29, and draw a line to intersect the rectangular curve. Sorry, and we can get that. Oh, sorry. So we can get that maybe the yn over the b is approximately to the 0.63, and we know the b equals 3 meters in this problem, so we can get that the yn equals 1.89 meters. So we have done this problem. For the last problem, uniform flow occurs in a 20 feet wide rectangular channel with a discharge of 2,520 cubic feet per second. If the normal depth of the flow is 15 feet, what will be the new normal depth when the width of the channel expands to 30 feet? Assume that the slope and the channel roughness remain constant in both channels. So for this problem, we apply Manning's equation in the British unit system. So the Q equals 1.49 over n times A times RH to the power of 2 over 3 times S to the power of 1 over 2. And since we know the RH equals A over P, so we can get that the Q equals 1.49 over n times A to the power of 5 over 3 times P to the power of negative 2 over 3 times S to the power of 1 over 2. And for the first rectangular channel, we know the A1 equals B1 times Y1, and P1 equals B1 plus 2Y1. And we know from the problem, the B1, the width of the first rectangular channel B1 equals 20 feet, and the Y1 equals 15 feet. So we can get that the A1 equals 300 cubic feet, and the P1 equals 50 feet. And for the second rectangular channel, the A2 equals B2 times Y2, and the P2 equals P2 plus 2 times Y2. The Y2 is the new north depth that we need to determine. And from the problem, we also know the B2 equals 30 feet. So we can determine that A2 equals 30 times Y2 square feet, and P2 equals 30 plus 2 times y2 feet. And since the discharge of these two rectangular channels should be equal, so we can get that 1.49 over the n times a1 to the power 5 over 3 times p1 to the power of negative 2 over 3 times s1 to the power of 1 over 2 equals 1.49 over the n times a2 to the power of 5 over 3 times p2 to the power of negative 2 over 3 times s2 to the power of 1 over 2. Since assume that the slope and the channel roughness remain constant in both channels, so we can eliminate this item. So we get that a1 to the power of 5 over 3 times p1 to the power of negative 2 over 3 equals a2 to the power of 5 over 3 times p2 to the power of negative 2 over 3. So, and we substitute the value, we can get that 300 square feet to the power of 5 over 3 times 15 feet to the power of negative 2 over 3 equals to 30 times y2 to the power of 5 over 3 times 13 plus 2y2 to the power of negative 2 over 3. And then use the successive substitution method, we can determine that y2 equals 10 feet. So we have done this problem.